In 2004, scientists mapped the oldest light in the universe and found something that should not exist. A patch of sky in the constellation Eridanus was too cold, not by a little, by enough to make physicists lose sleep. Then, years later, astronomers pointed their telescopes at that same region and discovered something hiding behind the anomaly. An enormous void. 1 billion light-years of almost nothing. The possibility that this void created the cold spot is not confirmed, but the hypothesis alone is enough to disturb the foundations of modern cosmology. Because if a structure that large can distort the oldest light in existence, then something about how we understand the universe may be deeply, fundamentally incomplete. If you enjoy deep explorations into the strangest corners of the cosmos, do me a small favour and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making content like this for you. Now, get yourself comfortable. Let's begin. The universe keeps a photograph of itself as an infant. It is not locked away in some restricted archive or hidden behind classified clearance levels. It is arriving at your location right now, at this exact moment, from every single direction in the sky, at the speed of light, without interruption, without pause, every second of every day. This photograph is the cosmic microwave background radiation, and it represents the oldest light that any telescope, any detector, any instrument ever built or ever conceived will detect. Nothing older can reach us through electromagnetic radiation. This is the wall, the boundary, the first visible surface of the universe's entire history. To understand why a strange cold patch in this ancient light terrifies some of the smartest people alive, you first need to understand what the cosmic microwave background actually is and why it matters so deeply to everything we think we know about the cosmos. Roughly 380,000 years after the Big Bang, the universe crossed a critical threshold. It had been expanding and cooling since the initial moment of creation. For all those hundreds of thousands of years, the cosmos was a blinding, opaque furnace. Space was filled with a thick plasma of free electrons, protons, and photons, all smashing into one another relentlessly. Light could not travel in a straight line. Every photon that tried to move through space immediately collided with a free electron and scattered in a random direction. The universe was a glowing fog, not dim, not faint. Searingly bright and utterly opaque in every direction. Nothing could see through it. Nothing could send a signal through it. The cosmos was a wall of light with no transparency whatsoever. Then the temperature dropped below approximately 3,000 degrees. Protons and electrons suddenly had little enough energy to combine and form stable hydrogen atoms for the first time. This event is called recombination, and it changed everything. When electrons bonded to protons, they stopped scattering photons. The fog cleared. Light was released in every direction simultaneously, flooding through newly transparent space like a dam breaking. Those photons have been travelling ever since. For 13.8 billion years, they have crossed the expanding universe, stretching as space itself stretched, losing energy as their wavelengths grew longer. What began as a blinding, visible and infrared glow has now been redshifted into microwave wavelengths. The temperature of this ancient light has cooled to approximately 2.725 Kelvin, a whisper above absolute zero, faint, cold, almost undetectable, but everywhere. Every cubic centimetre of space in the observable universe is filled with roughly 400 of these ancient photons. They outnumber the atoms in the universe by a factor of about 1 billion to 1. They carry information about the conditions that existed when the universe was less than 1% of its current age. They are the oldest messengers we will ever receive, and for decades the most powerful space agencies on Earth have been building instruments specifically designed to listen to what they have to say. The first confirmed detection of the cosmic microwave background happened almost by accident. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna at Bell Labs in Holmdel, New Jersey. They were trying to calibrate the instrument for satellite communication experiments, but they could not eliminate a persistent low-level hiss that appeared no matter where they pointed the antenna. They checked every possible source of interference. They removed pigeon nests from inside the horn. They cooled the receiver. They accounted for atmospheric noise. The hiss remained. It came from every direction in the sky. It was constant, uniform, and inexplicable. What Penzias and Wilson had stumbled upon was the afterglow of the Big Bang itself. Theoretical physicists had predicted this radiation years earlier. Robert Dicke and his team at Princeton were actually building a detector to search for it at the very same time Penzias and Wilson found it by accident. The discovery confirmed one of the most profound predictions of Big Bang cosmology and earned Penzias and Wilson the Nobel Prize in Physics. The universe had a beginning. It was once unimaginably hot and dense, and it left behind a faint thermal glow that permeates all of space. But detecting the background radiation was merely the opening chapter. The real scientific power of the cosmic microwave background lies not in its existence but in its details, and extracting those details required instruments far beyond anything available in 1965. The Cosmic Background Explorer satellite, known as COBE, launched in 1989 and provided the first full sky map of the CMB temperature. What COBE revealed was simultaneously reassuring and astonishing. The radiation was extraordinarily uniform. In every direction astronomers looked, the temperature registered at 2.725 Kelvin. The uniformity was so extreme, better than 1 part in 10,000, that it posed deep questions about why regions of space that had never been in causal contact with each other could share nearly identical temperatures. This problem, known as the horizon problem, became one of the motivations for the theory of cosmic inflation. But buried within that uniformity, COBE detected something else. Tiny temperature fluctuations, variations of roughly 1 part in 100,000 from one patch of sky to another. These were not instrument errors or foreground contamination from the Milky Way. They were real, and they were expected. Theory predicted that quantum fluctuations during inflation would create minuscule density variations in the primordial plasma. Regions slightly denser than average would be slightly hotter. Regions slightly less dense would be slightly cooler. These variations, imprinted onto the last scattering surface when the universe became transparent, should appear as faint temperature differences in the CMB. COBE confirmed that these fluctuations existed, but its angular resolution was too coarse to map them in fine detail. The scientific community needed sharper vision. The Wilkinson microwave anisotropy probe, known as WMAP, launched in 2001 aboard a Delta II rocket and settled into an orbit around the second Lagrange point, roughly 1.5 million kilometers from Earth. From this vantage point, far from the thermal interference of our planet, WMAP spent 9 years mapping the temperature of the cosmic microwave background across the entire sky with dramatically improved resolution. The result was a detailed portrait of the infant universe showing the pattern of hot and cold spots at angular scales down to about 1/4 degree. These maps became the backbone of precision cosmology. By analysing the statistical properties of the temperature fluctuations, their sizes, their relative amplitudes, and their spatial correlations, scientists could test detailed predictions about the universe's age, geometry, composition, and expansion history. The results were remarkable. The CMB data matched the predictions of the standard lambda cold dark matter model with extraordinary accuracy. The universe was 13.8 billion years old. It was geometrically flat. It contained roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Almost everything fit like interlocking pieces of a beautifully machined puzzle. Almost. In 2004, a team of researchers analysing the WMAP temperature maps identified something that did not fit. In the southern galactic sky, centred near the constellation Eridanus, there was a region where the CMB temperature dipped noticeably below the surrounding average. This region spanned roughly 5 to 10 degrees across the sky, depending on the filtering method used to define its boundaries. For perspective, the full moon covers about 1/2 degree of arc. The anomalous region stretched across an area equivalent to 10 to 20 full moons laid side by side. In terms of CMB features, this was enormous. Most primordial fluctuations occupy much smaller angular scales. The temperature deficit within this region measured approximately 70 millionths of a degree below the CMB average. That number sounds laughably small in everyday terms. 70 millionths of a degree would be completely undetectable by any thermometer you have ever used. But the cosmic microwave background is a domain where laughably small numbers carry the weight of entire theoretical frameworks. The expected primordial fluctuations are themselves only about 100 millionths of a degree. A coherent deficit of 70 millionths in a patch this large was not something that standard inflationary models produced casually. It sat uncomfortably far out on the tail of the predicted probability distribution. The feature quickly acquired a name: the CMB Cold Spot. Simple, descriptive, and quietly ominous. Several independent research groups confirmed the anomaly using different analytical techniques. One of the most powerful methods involved wavelet analysis, a mathematical approach that isolates features at specific angular scales by filtering out both smaller and larger structures. When researchers applied spherical Mexican hat wavelet transforms to the WMAP data, the cold spot appeared as the single coldest feature on the entire CMB sky at the relevant angular scale. It was not merely one of several cold regions, it was the most extreme one. The statistical significance of the cold spot depends on how the analysis is framed, and this is where the scientific debate begins to sharpen. If you ask simply how likely it is to find a cold spot this deep anywhere on the CMB sky, the answer is roughly 1 to 2%. That means in 100 random realizations of the universe generated from standard inflationary initial conditions, only 1 or 2 would produce a feature as extreme as what we observe. 1 to 2% is not vanishingly improbable. Events with those odds happen in everyday life without attracting attention. You would not be shocked to draw a particular card from a deck if you had 50 attempts. But there is a subtlety that makes this probability more troubling than it first appears. The cold spot is not merely cold. Its profile, the specific way its temperature drops from the edges toward the center, does not closely match the profile expected from standard Gaussian random fluctuations. Primordial temperature fluctuations should follow a Gaussian distribution, meaning their statistical properties are entirely characterized by a two-point correlation function. The cold spot shows departures from this expectation. Its temperature gradient is steeper at certain radii. Its shape is more symmetric than typical cold features. Its depth relative to its angular extent is unusual. Any one of these properties taken individually might be unremarkable, but their combination in a single feature pushes the statistical discomfort higher. The Planck satellite, launched in 2009 by the European Space Agency, provided the definitive confirmation. Planck mapped the CMB with even greater sensitivity and angular resolution than WMAP, observing in 9 frequency bands spanning microwave to sub-millimeter wavelengths. This multi-frequency coverage allowed researchers to separate the true CMB signal from foreground contamination caused by our own galaxy's dust, gas, and synchrotron radiation with unprecedented precision. When the Planck team analysed their cleaned CMB maps, the cold spot was still there, unchanged, unmistakable. It was not an artifact of WMAP's instrument noise. It was not a residual from imperfect foreground subtraction. It was not a processing error. The feature was physically real and embedded in the cosmic microwave background radiation itself. Planck's data also allowed researchers to perform more sophisticated statistical tests. They examined the cold spot using multiple wavelet scales, higher-order statistical measures, and comparisons with thousands of simulated CMB skies generated from the best-fit cosmological parameters. The results consistently placed the cold spot in the outer 2 to 3% of the simulated distribution. Not impossible, but persistently unusual. The scientific community divided into several interpretive camps, and the divisions have persisted for 2 decades. The first camp argued that the cold spot is simply a statistical fluke. The CMB sky contains millions of independent resolution elements. When you examine that many data points, some will inevitably fall at the extremes of the probability distribution. This is the look elsewhere effect, a well-known statistical phenomenon. If you flip a fair coin 10,000 times, you will find long streaks of consecutive heads. Those streaks look improbable when examined individually, but are inevitable when considered within the full dataset. The cold spot, according to this interpretation, is the CMB's equivalent of a long streak, unusual when isolated, unremarkable when considered as one draw from an enormous statistical ensemble. This argument has genuine force. Cosmologists have only one sky to observe. Drawing strong conclusions from a single feature in a single realization of the universe is inherently risky. Posterior statistics, where you search a dataset for anomalies and then calculate the probability of finding them, are always less convincing than prior predictions that are subsequently confirmed. Nobody predicted the cold spot before it was found. It was discovered through data exploration, which means the probability calculations are subject to significant look elsewhere corrections. The second camp found this reasoning insufficient. They pointed out that the cold spot is not anomalous in just one statistical measure. It appears extreme across multiple independent tests. Its depth, its angular extent, its temperature profile, its kurtosis, and its wavelet coefficient all sit in the tails of their respective distributions simultaneously. While any single deviation might be dismissed as a fluke, the conjunction of several deviations in the same spatial feature raises the collective improbability considerably. The probability of finding a feature that is simultaneously this cold, this wide, and this steep profiled drops well below the 1 to 2% figure quoted for depth alone. Members of this camp also noted a pattern. The cold spot is not the only unusual feature in the CMB. Researchers have identified several other low-level anomalies in both WMAP and Planck data, features that individually sit at marginal significance, but collectively suggest the microwave background may contain patterns that the simplest inflationary models do not comfortably predict. The cold spot is the most visually striking of these features, and the one most directly linked to a potential physical explanation. A third interpretation emerged that shifted the entire framing of the question. What if the cold spot was not entirely a primordial feature? What if something between us and the surface of last scattering had altered the CMB photons as they travelled toward Earth? This idea is not speculative. It is grounded in well-established physics. The cosmic microwave background photons have been travelling for 13.8 billion years. During that immense journey, they have passed through every structure that formed along their path. Galaxy clusters with deep gravitational wells, filaments of the cosmic web, and voids. Vast, underdense regions where matter is sparse and gravity is weak. Each of these structures can imprint subtle signatures onto the CMB through known gravitational effects. If a sufficiently large void happened to lie along the line of sight toward the cold spot, it could modify the energy of passing CMB photons through a mechanism called the integrated Sachs-Wolfe effect. This effect, predicted in 1967, describes how photons gain or lose energy when the gravitational potential they are traversing changes during their passage. In a universe where dark energy drives accelerating expansion, the gravitational potentials of large voids decay over time. Photons passing through such an evolving void lose net energy, arriving at Earth slightly redshifted, which registers as a temperature decrement in the CMB map. This possibility opened an entirely new line of investigation. Instead of staring exclusively at the CMB, astronomers began looking in the foreground. They turned their attention to the three-dimensional distribution of matter in the direction of the Eridanus cold spot. If a void was responsible for even part of the anomaly, it should be detectable through galaxy surveys. Fewer galaxies in that direction at a specific distance range would signal an underdense region. A deficit of radio sources would corroborate the finding. The void, if it existed, would be enormous. But it would be findable, and this is where the cold spot story takes its most consequential turn. Because the astronomers went looking, and they found something. What they discovered in the direction of the cold spot was not a modest underdensity. It was not a run-of-the-mill gap between galaxy clusters. It was a structure so large that it challenged easy comprehension, a region of space stretching across a significant fraction of a billion light-years where galaxies were conspicuously sparse, a void on a scale that sits at the outer edge of what standard cosmological models predict should exist. The alignment between this void and the cold spot was geometrically precise. The angular position on the sky matched. The void sat at a distance where the integrated Sachs-Wolfe effect would be relevant. The physics connecting the two was straightforward and well understood. Everything pointed toward a connection. But nothing in this story resolves cleanly. The void's properties, its exact size, its depth, its density profile, remain subjects of active measurement and debate. Different survey datasets produce somewhat different characterizations. And the most critical question of all, whether a void of the observed properties can quantitatively account for the cold spot's temperature deficit, would deliver an answer that pleased almost nobody. The cold spot had drawn a line in the cosmic sand. On one side stood the possibility that the universe's oldest light carries a scar inflicted by an enormous foreground structure, a scar that known physics can partially but not fully explain. On the other side stood the possibility that the anomaly is primordial, a relic of conditions at the birth of the cosmos that the standard model does not comfortably accommodate. Between those two possibilities lies a gap, and that gap is where the real discomfort lives, not in what we know, but in what we cannot yet distinguish. But before we can evaluate that connection, we need to understand what cosmic voids actually are, how they form, and why a void of the size associated with the cold spot is itself a deeply strange object. Because the void is not just a possible explanation for the anomaly, it is an anomaly of its own. The universe is not what it looks like. Point a telescope at the night sky and you see light, stars, galaxies, nebulae glowing in colours that span the electromagnetic spectrum. Every image from every observatory reinforces the same visual impression. The cosmos is full of stuff. Luminous, energetic, densely packed stuff. Peer deeper with more powerful instruments and you find more of the same. Galaxies behind galaxies behind galaxies, stretching to the limits of detection. The Hubble Ultra Deep Field revealed roughly 10,000 galaxies in a patch of sky smaller than a grain of sand held at arm's length. The James Webb Space Telescope pushed even further, finding galaxies so distant their light has been travelling for over 13 billion years. The universe appears inexhaustibly full, but this impression is one of the great optical illusions in nature. What you are actually seeing when you look at the night sky is the exception. The rare part, the thin, bright thread stitched through an overwhelming darkness. The universe is not mostly galaxies. It is mostly nothing. And the nothing is not a passive backdrop waiting to be filled. It is a structure in its own right, with its own physics, its own evolution, and its own capacity to leave marks on the oldest light in existence. Cosmic voids are the dominant environment in the universe. They occupy roughly 60% of the total volume of space by conservative estimates, and some calculations push that figure closer to 80%. They are not simply the gaps between interesting things, they are the most common terrain in the cosmos, and everything else, every galaxy, every cluster, every luminous filament of the cosmic web, exists as a minority feature, embedded within or draped around these vast empty regions. If the universe were an ocean, galaxies would not be the water. They would be the thin foam riding on top of waves. The water itself, the overwhelming majority of the volume, would be void. Understanding voids is not optional for understanding the universe. It is prerequisite. To grasp what voids are, and why one particular void has become linked to one of the most unsettling anomalies in modern cosmology, you first need to understand the architecture they inhabit. You need to see the cosmic web. For most of human history, the distribution of galaxies beyond our own appeared random. Early sky surveys showed galaxies scattered across the heavens in no obvious pattern. Some clustered together in groups and clusters, while others seemed to float alone. There was no reason to suspect any grand organizing principle. The universe looked, from our vantage point, like confetti tossed across a dark tablecloth. That picture shattered in the late 1970s and 1980s when astronomers began conducting systematic redshift surveys. A redshift survey does more than photograph galaxies. It measures how much the light from each galaxy has been stretched by cosmic expansion, which reveals the galaxy's distance from Earth. Combining angular positions on the sky with distance measurements produces a three-dimensional map of where galaxies actually sit in cosmic space. And when the first large redshift surveys returned their results, the confetti turned out to be anything but random. In 1978, Stephen Gregory and Laird Thompson published one of the first maps showing large-scale galaxy clustering, revealing that galaxies were not scattered uniformly but concentrated along elongated structures with conspicuous gaps between them. Shortly after, in 1981, Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman identified the Botas Void, a region roughly 330 million light-years across, containing far fewer galaxies than surrounding volumes. The emptiness was startling. A sphere of space large enough to swallow thousands of galaxies, and yet almost barren. But the full revelation came with the Center for Astrophysics Redshift Survey, led by Margaret Geller and John Huchra, which mapped the positions of thousands of galaxies across a wedge-shaped slice of the nearby universe. The resulting map, published in 1986, became one of the most iconic images in the history of astronomy. It showed galaxies arranged not in random clumps but along thin walls and filaments that surrounded enormous empty bubbles. The pattern looked like soap foam, dense walls of galaxies enclosing vast hollow interiors. Subsequent data from the same survey revealed even larger features, including a sheet of galaxies stretching across roughly 500 million light-years that was dubbed the Great Wall. The cosmic web had revealed itself, and the voids were not minor features within it. They were the defining geometry. The filaments and walls existed because the voids existed. The dense structures marked the boundaries of the empty regions, like the membranes of bubbles in a bath. Take away the voids and the web collapses. There is no filamentary structure without the emptiness that shapes it. The voids are the scaffolding, and the galaxies are the decoration hung upon it. Subsequent surveys expanded this picture to ever larger scales and ever greater detail. The 2-degree field galaxy redshift survey, completed in 2003, mapped over 200,000 galaxies across a significant fraction of the sky. The Sloan Digital Sky Survey, which began observations in 2000 and has continued in various phases for over 2 decades, mapped millions of galaxies across billions of light-years. Each survey confirmed and extended the same basic architecture: filaments of galaxies tens of millions of light-years long, connecting galaxy clusters at the nodes where multiple filaments converge. Walls and sheets where filaments intersect to form 2-dimensional surfaces, and between them all, the voids, dark bubbles ranging from tens of millions to hundreds of millions of light-years across, defined not by what they contain but by what they lack. The 3-dimensional maps produced by these surveys are among the most visually striking products of modern science. They reveal a universe that looks disturbingly biological. The filaments branch and twist like blood vessels or neural networks. The nodes pulse with dense concentrations of galaxies like synaptic junctions. The voids sit between them like the spaces inside a sponge. The resemblance to organic structures is not coincidental. Both biological networks and cosmic networks form through processes that create branching, hierarchical patterns. Gravity sculpts the cosmic web through the same mathematical principles that govern how rivers carve drainage basins and how crystals grow along preferred lattice directions. The universe organizes itself through simple rules applied across vast scales, and the resulting geometry echoes patterns found throughout nature. But the cosmic web's elegance conceals a fundamental asymmetry. The dense structures, the filaments and clusters that contain the overwhelming majority of galaxies, occupy a small minority of the total cosmic volume. Different analyses produce slightly different numbers, but the general picture is consistent. Filaments and walls account for perhaps 10 to 20% of the volume, while containing the vast majority of the matter. Voids account for 60 to 80% of the volume, while containing a small fraction of the total mass. The universe is a structure built mostly out of absence. A cosmic void is a region of space where the density of matter falls significantly below the cosmic average. The term sounds clean and absolute, but the reality is messier. Voids do not have sharp walls. They do not possess clear boundaries like rooms in a building. They fade. The density of galaxies decreases gradually as you move from the filaments of the cosmic web into the interior of a void. At some point, the count drops low enough that astronomers draw a line and say this region qualifies as underdense. But the exact placement of that line depends on the definition used, the survey depth, the statistical method applied, and the criteria of the research group doing the counting. Two teams studying the same region of sky can produce different void catalogues, not because either is wrong, but because the structures themselves resist crisp demarcation. Despite this fuzziness at the edges, the interiors of voids are genuinely sparse. A typical void might contain 20 to 40% less matter than the cosmic average. Some contain even less. The galaxies that do exist within voids tend to be small, faint, and profoundly isolated. Dwarf galaxies and dim spirals drifting through enormous volumes of space with no significant neighbours for tens of millions of light years in any direction. If you could somehow transport yourself to the centre of a large void and look out in every direction, the sky would be almost empty. A handful of faint smudges marking the locations of distant, lonely galaxies. No bright clusters, no rich superclusters, no crowded fields of stars belonging to nearby neighbours, just space stretching away into darkness for distances that dwarf the diameter of our entire local group. These void galaxies evolve differently from their counterparts in dense environments. Galaxies in clusters and filaments experience frequent gravitational interactions with neighbours. They collide, merge, strip gas from one another, trigger violent bursts of star formation, and grow rapidly through cannibalism. A galaxy in a dense region lives a turbulent life, shaped as much by its environment as by its own internal processes. Void galaxies experience none of this. They retain their gas reservoirs because nothing strips the gas away. They form stars at modest rates over extended periods rather than in the dramatic bursts triggered by collisions. They maintain their disk structures and spiral arms because no gravitational encounter has disturbed them. Void galaxies are the hermits of the cosmos, quietly aging in solitude while the dense filaments and clusters around them roil with mergers and interactions. Studying them provides a baseline for understanding what galaxy evolution looks like in the absence of environmental influence, a control experiment that nature provides for free. The origin of cosmic voids reaches back to the same primordial process that created all large-scale structure. In the first fraction of a second after the Big Bang, during the epoch of cosmic inflation, quantum fluctuations were stretched from subatomic scales to cosmological scales. These fluctuations created tiny variations in the density of matter and energy throughout the infant universe. Some regions ended up fractionally denser than average. Others ended up fractionally less dense. The differences were minuscule, roughly 1 part in 100,000, a density variation so small that no instrument on Earth could detect it in any laboratory setting. But gravity is patient and relentless. Over hundreds of millions of years, it amplified these seed variations through a process called gravitational instability. The mechanism is elegant in its simplicity. A region that begins slightly denser than its surroundings exerts a marginally stronger gravitational pull. Matter from adjacent areas falls toward it, adding to its mass. The increased mass strengthens the gravitational pull further, drawing in more matter from even greater distances. This positive feedback loop operates continuously over cosmic time. The denser a region becomes, the faster it grows. Small clumps merge into larger clumps, which merge into galaxy mass concentrations, which assemble into groups, which combine into clusters, which align into the filaments and walls of the cosmic web. Structure builds from the bottom up, with gravity relentlessly pulling matter toward the densest regions. Meanwhile, the regions that started slightly underdense experienced the mirror image process. They lost matter to their denser neighbours. As material drained away toward the growing overdensities, the underdense regions became emptier. Less matter meant less gravitational pull to retain what remained, which allowed more matter to escape. This negative feedback hollowed out the underdense regions progressively over cosmic time, creating the voids we observe today. Where gravity builds mountains in the dense regions, it excavates valleys in the sparse ones. The cosmic web is the result of both processes working simultaneously, constructing filaments and emptying voids in a single coordinated evolution, driven by the same initial conditions and the same physical law. Dark energy accelerated the emptying. In regions where matter is abundant, gravity can resist the expansion of space to some degree. Galaxy clusters, for instance, are gravitationally bound systems that hold themselves together despite the universe expanding around them. The Virgo cluster, the Coma cluster, the Perseus cluster, these massive concentrations of galaxies collapsed out of the expanding background billions of years ago and have maintained their structural integrity ever since. Gravity wins the local tug-of-war against cosmic expansion in these dense environments. But inside voids, gravity has little ammunition to fight back. The matter density is too low to generate gravitational forces capable of resisting expansion. Dark energy, the mysterious component that drives accelerating cosmic expansion and comprises roughly 68% of the universe's total energy content, dominates the physics of void interiors more thoroughly than anywhere else in the observable cosmos. Voids expand faster than the cosmic average. They inflate like slow-motion balloons pressed between the denser structures of the cosmic web. As they expand, the matter within them spreads thinner. The density drops further. The gravitational resistance weakens. The expansion accelerates. The cycle is self-reinforcing. Voids grow, and they have been growing for billions of years. This makes void interiors some of the most extreme environments in nature. Not extreme in the way that a black hole's event horizon is extreme, or the surface of a neutron star, or the core of a supernova. Those are environments of extreme density, extreme energy, extreme violence. Voids are extreme in the opposite direction. They are environments of extreme emptiness, extreme calm, extreme gravitational silence. If you wanted to find a place in the universe where dark energy's influence is least contaminated by the effects of matter and gravity, a place where the accelerating expansion of space proceeds with minimal interference, you would go to the center of a large void. These regions are the purest dark energy laboratories in existence, and the physics that operates within them, the stretching of space, the flattening of gravitational potentials, the slow draining of energy from photons passing through, is directly relevant to the mystery of the cold spot. The typical cosmic void spans somewhere between 100 and 300 million light-years in diameter. These are common features of the cosmic web, predicted reliably by computer simulations of structure formation and confirmed by every major galaxy redshift survey conducted since the 1980s. They are expected. They are understood. They fit comfortably within the standard cosmological model, but not all voids are typical. The Boyt's void, identified in 1981, was one of the first to attract sustained scientific attention. Spanning roughly 250 million light-years in diameter, it contained far fewer galaxies than a region that size should hold according to the cosmic average density. When it was first discovered, it appeared almost impossibly empty. A sphere of space that should contain thousands of galaxies held barely 60. Subsequent deeper surveys found a few additional galaxies scattered through its interior, faint dwarfs hiding below the detection limits of earlier instruments. But the overall density remained dramatically below average. The Boyt's void demonstrated that the universe was capable of producing enormous empty regions, and its discovery prompted a generation of surveys designed to map the void population systematically. The local void, characterized in detail by Brent Tully and colleagues in 2008, sits much closer to home. It lies adjacent to our own galaxy, beginning just beyond the boundaries of the local group. The local void spans roughly 200 million light-years and is notable for its influence on the Milky Way's motion through space. Our galaxy is not stationary relative to the cosmic microwave background. It moves at roughly 630 kilometers per second in a direction determined by the combined gravitational pull of surrounding structures. Part of that motion comes from attraction toward the dense concentrations of the Virgo cluster and the Greater Tractor region, but part of it comes from the gravitational push of the local void. The deficit of matter inside the void means less gravity pulling us toward it, which effectively pushes us away. The void repels not through any exotic force, but through the simple absence of the gravitational attraction that would otherwise balance our motion. We are being pushed by nothing. The emptiness itself has dynamical consequences that shape how our galaxy moves through the cosmos. Other voids have contributed important pieces to the evolving picture. The sculptor void, the Eridanus void, the microscopium void, each one catalogued and characterized through galaxy counts and redshift measurements. Void catalogues now contain thousands of entries, mapped across billions of light-years of surveyed volume. These catalogues reveal the statistical properties of the void population, their size distribution, their depth distribution, their shapes, their clustering properties, their relationship to the surrounding cosmic web. The statistics match the predictions of lambda-cold dark matter simulations with reasonable fidelity for voids in the typical size range. At the extreme end of the size distribution lie the supervoids. These are structures that stretch beyond 500 million light-years, sometimes exceeding 1 billion light-years in diameter. They are rare. Computer simulations based on standard cosmological initial conditions produce them infrequently. The probability of finding a supervoid of a given size depends sensitively on the amplitude of primordial density fluctuations, the matter density of the universe, and the properties of dark energy. Standard simulations can produce supervoids, but the largest and deepest ones appear only in a small fraction of simulated cosmic volumes. The rarity matters. Every observed supervoid carries implicit information about whether the standard model's predictions for the tail of the structure formation distribution are correct. If the real universe contains more large supervoids than simulations produce, either the simulations are missing something, or the universe's initial conditions were different from what the standard model assumes. The KBC void, named after its discoverers Keenan, Barger, and Cowie, who published their analysis in 2013, represents perhaps the most provocative example. Their galaxy counts suggested that the Milky Way and its surrounding cosmic neighborhood might reside within a vast, underdense region roughly 2 billion light-years in diameter, with a density deficit of approximately 20% below the cosmic average. If confirmed at these parameters, the KBC void would be one of the largest coherent structures ever identified, and our position near its center would have implications for how we interpret local measurements of cosmic expansion. The KBC void remains actively debated, with different research groups finding different characterizations of its extent and depth, but its potential existence highlights how supervoids are not merely cosmological curiosities. They are structures with the power to bias fundamental measurements. It was against this backdrop of growing void science that astronomers turned their attention to a specific region of the southern sky, the direction of the CMB Cold Spot in the constellation Eridanus. If the cold spot had a foreground explanation, a void along the line of sight was the most physically motivated candidate. The integrated Sachs-Wolfe effect provided the mechanism. The question was whether a void of sufficient size and depth actually existed in that direction. In 2007, Lawrence Rudnick and colleagues at the University of Minnesota published a study that transformed the cold spot debate from a purely CMB-focused investigation into a multi-wavelength hunt for foreground structure. Using data from the NRAO VLA Sky Survey, one of the most comprehensive radio source catalogues available at the time, Rudnick's team examined the distribution of extragalactic radio sources in the direction of the cold spot. Radio galaxies are not randomly distributed through space. they trace the underlying matter distribution. Where matter is dense, radio sources are abundant because dense environments contain more massive galaxies, more active galactic nuclei, and more of the energetic phenomena that produce strong radio emission. Where matter is sparse, radio source counts drop. Rudnick's group found a significant deficit of radio sources in the Eridanus Cold Spot direction compared to surrounding regions of the sky. The deficit was not subtle. It represented a clear, measurable reduction in source counts over an angular area broadly corresponding to the cold spot itself. The implication was immediate and provocative. If radio galaxies were scarce in that direction, a large underdense region likely existed along the line of sight. And if that void was large enough and deep enough, it might be physically connected to the CMB temperature anomaly. The study was contested almost immediately. Some researchers argued that the radio source deficit might result from observational selection effects or incomplete sky coverage in the survey. Others questioned whether the statistical methods used to quantify the deficit were robust enough to claim a genuine void detection. Radio source counts can be affected by variations in survey sensitivity across the sky, by calibration differences between different observing runs, and by contamination from galactic foreground sources that must be carefully masked. Disentangling a genuine cosmological underdensity from these observational effects is not trivial, but the Rudnick study accomplished something important regardless of these caveats. It established the void hypothesis as a serious, testable alternative to purely primordial explanations for the cold spot, and it motivated a wave of follow-up investigations using independent datasets and different observational techniques. The breakthrough study came in 2015, when a team led by Istvan Sapudi at the University of Hawaii published results that brought the Eridanus Supervoid into substantially sharper focus. Sapudi's group took a fundamentally different approach from Rudnick. Instead of counting radio sources, they used galaxy surveys in optical and infrared wavelengths to construct a three-dimensional map of the matter distribution in the cold spot direction. The method relied on photometric redshift estimation, a technique that uses the colors of galaxies rather than their spectral lines to estimate their distances. When light from a distant galaxy is stretched by cosmic expansion, its entire spectrum shifts toward redder wavelengths. By measuring the galaxy's brightness through multiple color filters and comparing the resulting color pattern to theoretical models of galaxy spectra at various redshifts, astronomers can estimate the galaxy's distance without obtaining a full spectrum. Photometric redshifts are less precise than spectroscopic redshifts, which measure individual spectral lines and can determine distances to within fractions of a percent. Photometric estimates typically carry uncertainties of several percent in redshift, corresponding to distance uncertainties of tens to hundreds of millions of light-years. But photometric surveys can measure redshifts for vastly more galaxies than spectroscopic surveys, because they require only imaging rather than the time-intensive process of dispersing each galaxy's light into a spectrum. This trade-off between precision and sample size makes photometric surveys ideal for detecting very large structures, where the sheer scale of the feature compensates for the imprecision of individual distance measurements. Sapudi's team combined data from the 2-micron all-sky survey, which mapped galaxies in near-infrared wavelengths, and the Wide-Field Infrared Survey Explorer, which provided photometry across a broader infrared range. They supplemented these with optical data from the Pan-STARRS survey, a wide-field imaging program operated from Hawaii. By combining photometry across multiple wavelengths, they improved the accuracy of their redshift estimates and constructed a three-dimensional galaxy density map spanning the cold spot region. What they found was a large coherent underdensity centered at a photometric redshift of approximately 0.22. In cosmological terms, this corresponds to a co-moving distance of roughly 3 billion light-years from Earth. The structure was enormous. Its estimated diameter was approximately 1.8 billion light-years. Its density deficit was estimated at roughly 20% below the cosmic average, though the precise figure carried significant uncertainty depending on how the void's boundaries were defined and which density profile model was fitted to the data. The angular alignment between this supervoid and the cold spot on the CMB sky was striking. The void's projected position on the sky coincided with the cold spot within the observational uncertainties. Its angular extent was broadly consistent with the angular size of the temperature anomaly. The geometry practically demanded that the two features be physically connected, but characterizing a structure this large from galaxy survey data is not straightforward, and the difficulties deserve careful attention because they bear directly on whether the void can explain the cold spot. At a distance of 3 billion light-years, galaxy surveys become significantly less complete. Faint galaxies, which vastly outnumber bright ones, drop below detection thresholds. The surveys preferentially detect the brightest, most massive galaxies while missing the numerous smaller ones that populate the void's interior. This incompleteness means that the measured galaxy count in the void direction is a lower bound on the true galaxy population. The density deficit inferred from galaxy counts might overestimate the true matter deficit if the missing galaxies are distributed uniformly, or it might underestimate it if faint galaxies are even scarcer inside voids than outside them. Correcting for incompleteness requires assumptions about the luminosity function of void galaxies, which is itself uncertain. Photometric redshift uncertainties compound the problem. An uncertainty of several percent in redshift at this distance corresponds to a positional uncertainty of roughly 100 to 200 million light-years along the line of sight. This blurring makes it difficult to determine the void's precise extent in the radial direction. Is the void genuinely 1.8 billion light-years across, or is it a somewhat smaller structure smeared out by redshift errors? The difference matters because the ISW signal depends on the void's physical size. A smaller void produces a weaker temperature decrement. The boundaries of the void compound ambiguity further. Real voids do not have sharp edges. They transition gradually from underdense interior to average density surroundings over distances of tens to hundreds of millions of light-years. Where you place the boundary depends on your definition. Some researchers define the void edge as the radius where the density first reaches the cosmic average. Others use the point where it reaches half the average deficit. Still others define voids geometrically using watershed algorithms that partition space into void and non-void regions based on density topology. Each definition produces a different measured size and depth for the same underlying structure. These measurement challenges explain why different research groups studying the Eridanus Supervoid have produced somewhat different characterizations. Some find a density deficit closer to 15%. Others find values approaching 30%. Some place the void's center slightly offset from the cold spot's center on the sky. Others find closer alignment. Some identify the structure as a single coherent underdensity. Others see evidence for a more complex topology, perhaps multiple voids aligned along the same line of sight rather than one monolithic structure. These discrepancies are not contradictions. They reflect the genuine difficulty of measuring a diffuse billion light-year scale structure using surveys that sample the galaxy population incompletely at that distance. The basic finding has been confirmed by multiple independent groups using independent datasets. A significant underdensity exists in the Eridanus direction at roughly the right distance and angular position to be associated with the cold spot. The disagreements concern the void's precise properties, not its existence. A 2017 study by Mackenzie and colleagues used data from the Dark Energy Survey, a deep photometric survey covering a large area of the southern sky, to examine the galaxy distribution in the cold spot direction. Their analysis found evidence consistent with the Supervoid detection, identifying a significant underdensity at a similar redshift, though with somewhat different parameter estimates for the void's size and depth. The consistency across surveys strengthened the case that the void was real while highlighting the persistent uncertainties in its characterization. A 2017 analysis by Kovacs and colleagues took a different approach. Instead of simply characterizing the void, they examined the ISW signal associated with it by cross-correlating Planck CMB data with galaxy density maps. Their results supported a physical connection between the void and the cold spot, finding a temperature decrement in the CMB coincident with the galaxy underdensity. but the amplitude of the signal they measured exceeded standard ISW predictions for a void of the estimated properties, a result that added a new layer of complexity to the debate. Other researchers approached the problem from the opposite direction, starting with cosmological simulations rather than observations. They generated simulated universes using standard lambda cold dark matter initial conditions, identified the largest voids in those simulations, calculated their expected ISW signatures, and compared the results to the observed cold spot. These simulation-based analyses generally found that voids matching the Eridanus Supervoid's properties could account for a significant fraction of the cold spot's temperature deficit, but not all of it. The shortfall was consistent across multiple independent simulation efforts, suggesting that it reflected a genuine limitation of the void explanation rather than a peculiarity of any single analysis. The scale of the Eridanus Supervoid deserves deliberate attention because it carries implications far beyond its connection to the cold spot. A void approximately 1.8 billion light-years across, if confirmed at the upper end of current estimates, ranks among the largest individual underdense structures ever detected in the observable universe. To convey what that scale means in physical terms, light departing from one edge of this void, travelling at 300,000 kilometers per second, the fastest speed permitted by the laws of physics, would require roughly 1.8 billion years to reach the opposite edge. When that light began its journey across the void, the most complex life on Earth consisted of single-celled organisms. Multicellular life had not yet appeared. The void is so large that its light crossing time exceeds the entire history of complex biology on this planet. A photon from the cosmic microwave background passing through this void does not make a brief transit. It spends a cosmologically significant amount of time inside the structure. Hundreds of millions of years of travel through an environment where dark energy dominates. Gravity is feeble, and the gravitational potential is slowly flattening under the relentless stretching of space. Every moment of that transit contributes incrementally to the integrated Sachs-Wolfe effect. The photon accumulates a tiny energy deficit with each passing megaparsec, like a ball rolling across a landscape that is being gradually leveled while it moves. The void is also sufficiently large that its internal physics differs meaningfully from the cosmic average. Within its interior, dark energy dominates even more thoroughly than it does in typical regions of space. Gravity, already the weakest fundamental force, becomes even less relevant when the matter providing it is spread so thin. Structures within the void, the scattered dwarf galaxies and sparse gas clouds, evolve under conditions fundamentally different from those in dense filaments and clusters. Star formation proceeds at reduced rates. Galaxy interactions are almost non-existent. The gravitational potential is shallow and slowly flattening as dark energy continues to stretch the void outward. The existence of the Eridanus Supervoid also raises a question that has nothing to do with the cold spot. How rare is such a structure under the standard cosmological model? This question matters independently of the CMB anomaly because it tests the predictions of lambda cold dark matter for the extreme tail of the structure formation distribution. Computer simulations of structure formation produce a specific statistical distribution of void sizes and depths. Small voids, spanning a few tens of megaparsecs, are common. They arise from modest primordial underdensities and are produced reliably in every simulation volume. Medium voids, spanning 100 to 200 megaparsecs, are less common but routinely generated in simulation volumes comparable to the observable universe. Supervoids exceeding 500 megaparsecs are genuinely rare, and structures approaching or exceeding 1 billion light-years in diameter sit far out on the tail of the distribution, appearing only in a small percentage of simulated cosmic volumes. The exact frequency depends on multiple factors. Larger simulation volumes contain more opportunities for rare structures to form, so the probability of finding at least one supervoid increases with the survey volume. Higher amplitude primordial fluctuations produce more extreme structures at all scales, including larger voids. The assumed dark energy properties affect how voids evolve over cosmic time, with stronger dark energy producing faster void growth and potentially larger final sizes. Within the range of currently acceptable cosmological parameters, simulations can produce voids broadly matching the Eridanus Supervoid's properties, but they do so rarely. Most analyses place the structure somewhere between the uncommon and the genuinely improbable, depending on the precise parameter values assumed. If the Eridanus Supervoid is as large and deep as the more extreme observational estimates suggest, its existence constitutes a mild but genuine challenge to the standard model's predictions for structure formation. Not a crisis, not a refutation, but a data point that sits uncomfortably far from the center of the predicted distribution. If future surveys confirm more modest properties, the tension relaxes. If they confirm the extreme values, the tension sharpens. This is the peculiar position the Eridanus Supervoid occupies in modern cosmology. It is simultaneously a potential explanation for one anomaly and a potential anomaly in its own right. It might resolve the cold spot mystery by providing a known physical mechanism that partially accounts for the temperature deficit. But it might also deepen the mystery by representing a structure that standard models struggle to produce with comfortable frequency. The explanation and the problem are entangled in a way that resists clean separation. The underdensity is confirmed. Independent datasets spanning radio, infrared, and optical wavelengths all find a significant deficit of galaxies in the Eridanus direction at the appropriate distance. The alignment with the cold spot on the sky is real and not attributable to data processing artifacts, foreground contamination, or instrumental effects. Whatever is causing the cold spot, this void is physically present along the line of sight. What remains uncertain is whether this void can do what the cold spot seems to demand of it. Can a structure of these properties, filtered through the integrated Sachs-Wolfe mechanism, actually produce a temperature deficit of the observed magnitude? The answer to that question depends on physics that is well understood in principle, but fiendishly difficult to apply with precision in practice. It depends on how photons interact with evolving gravitational potentials as they traverse billion light-year stretches of underdense space. It depends on whether the standard ISW calculation captures the full complexity of the void's structure, and it depends on whether the void acts alone or whether additional effects, primordial fluctuations, secondary foreground structures, nonlinear gravitational dynamics, or something else entirely, are required to account for the full signal. The mechanism that connects voids to CMB temperature is elegant, grounded in general relativity and well supported by observational evidence. But applying it to a single specific void of extraordinary scale and asking whether it quantitatively reproduces a single, specific temperature anomaly requires a level of precision that current data cannot fully deliver. The distance between what the void can plausibly contribute and what the cold spot actually shows is the space where the real scientific tension lives. Understanding that tension requires a careful examination of the integrated Sachs-Wolfe effect itself, how it works, what it predicts for a void of this scale, and why the predictions fall short of the observation in ways that continue to trouble the researchers who study them most closely. The void has been found. The cold spot has been confirmed. The alignment is real. Now we need to follow the physics that connects them and confront the uncomfortable arithmetic that follows. Light does not simply pass through the universe unchanged. Every photon that travels across cosmological distances carries the imprint of its journey, not just the signature of where it was born, but the accumulated fingerprints of every gravitational environment it traversed along the way. The cosmic microwave background is often described as a snapshot of the infant universe, and it is. But it is a snapshot that has been handled by billions of years of cosmic structure. The light has been touched, subtly, almost imperceptibly, but measurably, and the mechanism by which an enormous void can leave its mark on that ancient light is not exotic. It is not speculative. It is general relativity doing precisely what Einstein's equations say it should do in an expanding universe dominated by dark energy. The integrated Sachs-Wolfe effect was first described by Rainer Sachs and Arthur Wolfe in a 1967 paper that explored how gravitational potentials influence the energy of photons in a cosmological context. The core idea is deceptively simple but carries profound consequences when applied to structures the size of the Eridanus Supervoid. Consider a photon travelling through space. It is a massless particle, but it is not immune to gravity. General relativity tells us that gravity is not a force pulling on objects through empty space. Gravity is the curvature of space-time itself. Mass and energy warp the geometry of space, and everything moving through that geometry, including light, follows the curved paths that the geometry dictates. When a photon approaches a concentration of mass, it falls into the gravitational potential well created by that mass. As it falls in, it gains energy. Its wavelength shortens. It blue shifts. When it climbs back out of the well on the other side, it loses energy. Its wavelength lengthens. It red shifts. In a perfectly static universe, these two effects would cancel with mathematical precision. The energy gained on the way in would exactly equal the energy lost on the way out. The photon would emerge from the gravitational well with precisely the same energy it had before entering. No net effect, no imprint. The structure would be invisible to the photon's energy budget, but the universe is not static. It has been expanding since the Big Bang, and for the past several billion years, that expansion has been accelerating under the influence of dark energy. This acceleration changes the calculation in a critical way. When a photon enters a gravitational potential well in an expanding universe, it gains energy as before. But while the photon is inside the well itself is evolving. If the structure is a dense region like a galaxy cluster, its self-gravity can resist cosmic expansion and maintain or even deepen its potential well. In that case, the well is roughly the same depth when the photon exits as when it entered, and the energy gain and loss still approximately cancel. Voids present the opposite situation. A void is an underdense region with a shallow gravitational potential. It lacks the concentrated mass needed to resist cosmic expansion. Dark energy dominates its internal physics. While the photon is traversing the void, the expansion of space stretches the void, making it even less dense, flattening its already shallow gravitational potential further. The well that the photon must climb out of when it exits the void is shallower than the well it fell into when it entered. At first glance, this might seem like it should give the photon a net energy gain. It fell into a deeper well and climbed out of a shallower one. But the effect works in the opposite direction for underdense regions. The key is that a void represents a gravitational potential hill relative to the denser surroundings, not a well. Photons entering a void are climbing upward out of the surrounding denser environment, losing energy as they ascend. While inside the void, the potential hill flattens because the void is expanding and becoming less distinct from its surroundings. When the photon exits, it descends a shallower slope than the one it climbed. The net result is that the photon loses energy during the transit. It arrives slightly redshifted. In temperature terms, it registers as slightly cooler than it would have been had the void not been there. The word integrated in the name refers to the fact that this effect is not instantaneous. It accumulates continuously along the photon's entire path through the evolving gravitational potential. A photon spends a finite amount of time inside any given structure, and the total energy change depends on how much the potential evolves during that transit time. Larger structures produce stronger effects because the photon spends more time inside them, allowing more opportunity for the potential to change. Deeper voids produce stronger effects because the gravitational potential contrast between the void interior and the surrounding average density space is larger, creating a steeper gradient for the photon to traverse. This is the mechanism by which an enormous void can cool a patch of the cosmic microwave background. Photons from the surface of last scattering pass through the void on their way to Earth. They lose a tiny amount of energy during the transit. When those photons arrive at our detectors, they register as fractionally cooler than photons that traveled through average density space. The temperature difference is extraordinarily small, measured in millionths of a degree. But at the precision level of CMB science, a deficit of that magnitude against a background of fluctuations measured in 100 millionths of a degree is not trivial. It is a signal that demands explanation. The integrated Sachs-Wolfe effect is not a theoretical speculation awaiting confirmation. It has been detected observationally through statistical methods. Researchers identified the positions of hundreds of known voids and galaxy clusters in large-scale galaxy surveys. They then examined the CMB temperature at each of those positions. For voids, they found a systematic average temperature decrement. For clusters, they found a systematic average temperature increment. The average values matched predictions from lambda cold dark matter cosmology. The ISW effect is real, confirmed, and quantitatively consistent with the standard cosmological model when measured across large statistical samples. The question is whether the ISW effect from one specific void, the Eridanus Supervoid, can account for the temperature deficit observed at one specific location, the CMB Cold Spot. This is where the analysis moves from established physics to active, unresolved scientific debate. Several research groups have calculated the expected ISW signal from a void matching the Eridanus Supervoid's estimated properties. These calculations require specifying the void's size, depth, density profile, and redshift, then integrating the photon energy change along the line of sight through the evolving gravitational potential. The cosmological parameters, including the matter density, dark energy density, and Hubble constant, also enter the calculation because they determine how the void's potential evolves over time. The results converge on a consistent range. For a void approximately 1.8 billion light-years in diameter, with a density deficit of roughly 20%, centered at a redshift of approximately 0.22, the predicted ISW temperature decrement falls in the range of approximately 20 to 40 millionths of a degree. The exact value depends on the assumed density profile. A void with a sharp, well-defined edge produces a different signal than one with a gradual, diffuse transition to the surrounding cosmic web. A void with a uniform interior density produces a different result than one with a concentrated underdensity at its center. A spherical void produces a different pattern than an ellipsoidal one. These modeling choices matter because the predicted ISW signal varies by roughly a factor of 2, depending on which assumptions are adopted. 20 millionths of a degree at the conservative end, 40 millionths of a degree at the generous end. This range represents the systematic uncertainty inherent in trying to model a billion light-year scale structure from incomplete galaxy survey data. The cold spot's observed temperature deficit is approximately 70 millionths of a degree. The arithmetic is not encouraging. Even the most generous ISW calculations for the Eridanus Supervoid account for only about half to 60% of the observed signal. The conservative estimates account for less than a third. There is a gap, and that gap is the central problem of the void-cold spot connection. This shortfall has been the defining frustration of the research program for over a decade. The physics is sound, the void is real, the mechanism is confirmed, but the numbers fall short. The Eridanus Supervoid produces a real physical ISW signal that contributes meaningfully to the cold spot's temperature deficit. It is not negligible, it is not irrelevant, but it is not sufficient. Something else is needed to account for the remainder. Several avenues have been pursued to close this gap, and none has succeeded definitively. The most straightforward possibility is that the void is more extreme than current measurements indicate. If the density deficit is closer to 30% rather than 20%, or if the void's diameter exceeds 2 billion light-years, the ISW signal increases accordingly. Some observational studies have found parameter values at the higher end of the range. A deeper, larger void could potentially produce a signal of 50 to 60 millionths of a degree, substantially closing the gap with the observed cold spot. But pushing the void parameters toward these extremes is not free. It requires adopting measurements at the boundary of current observational uncertainty, and it raises the independent question of whether such an extreme void is compatible with standard structure formation predictions. Making the void large enough to explain the cold spot risks making it too large to be explained by the standard cosmological model. The solution to one problem threatens to become a new problem in its own right. A second possibility involves refining the ISW calculation itself. Standard analytic models treat the void as an isolated, spherically symmetric perturbation embedded in an otherwise homogeneous universe. Real voids are neither perfectly spherical nor perfectly isolated. They are connected to the surrounding cosmic web through transition zones, where the density gradually rises from the void interior to the filament average. They may contain substructure, smaller overdensities and underdensities within the larger void volume. The gravitational potential along a real photon's path is more complex than any idealized model captures. Some researchers have explored whether more realistic void geometries could enhance the ISW signal beyond what simple spherical models predict. The results from these investigations have been mixed. Non-linear corrections to the gravitational potential evolution, which become important when the density contrast is large, can modestly increase the predicted signal. The inclusion of a compensating overdense shell around the void, a feature commonly seen in simulations where matter displaced from the void piles up at its edges, can alter the temperature profile in ways that affect the comparison with the observed cold spot shape. But these refinements typically change the predicted signal by 10 to 30%, not by the factor of 2 needed to fully bridge the gap. A related line of investigation examines the Rees-Sciama effect, a non-linear extension of the ISW mechanism that accounts for the gravitational effects of structures that are evolving not just because of cosmic expansion, but because of their own internal dynamics. Voids that are actively expanding, deepening, and reshaping themselves produce additional photon energy changes beyond the linear ISW prediction. For modest underdensities like most cosmic voids, the Rees-Sciama contribution is negligible, but for very deep, very large structures, it could potentially add a meaningful increment to the total signal. Calculations for the Eridanus Supervoid suggest that the Rees-Sciama effect adds at most 10 to 15% on top of the linear ISW prediction. Helpful, but not transformative. A third avenue explores whether the cold spot's temperature deficit might result from the superposition of the void's ISW signal and an independent primordial fluctuation in the CMB itself. The cosmic microwave background is full of temperature variations left over from the primordial density field. Some patches of sky are slightly warmer than average, others are slightly cooler. If a moderately cold primordial fluctuation happened to lie behind the Eridanus Supervoid along the same line of sight, the two effects would add together. The ISW signal from the void would contribute 20 to 40 millionths of a degree. The primordial fluctuation would contribute the remainder needed to reach 70 millionths. The total observed cold spot would be a composite of two independent effects. This explanation is physically plausible. There is nothing that forbids a primordial fluctuation from coinciding spatially with a foreground void. The two features originate at vastly different cosmic epochs and through entirely different physical processes. Their spatial overlap would be coincidental, not causal. The probability of such a coincidence depends on how unusual the required primordial component is. If the void accounts for 30 to 40 millionths of a degree, the primordial contribution needs to be only 30 to 40 millionths, which is well within the normal range of CMB fluctuations. A cold spot of that depth and angular extent would not be statistically anomalous on its own. It would be a perfectly ordinary feature of the primordial temperature field. This composite explanation has an appealing economy. It does not require new physics. It does not require the void to be more extreme than observations suggest. It does not require modifications to general relativity or the ISW calculation. It simply requires a coincidence, two independent effects lining up along the same direction on the sky. The probability of this specific coincidence can be estimated, and while it is not high, it is not absurdly low either. Some analyses place it in the range of a few percent, depending on the assumptions used. But the composite explanation carries a philosophical cost that some researchers find uncomfortable. It explains the cold spot by invoking two separate causes, neither of which is fully responsible on its own. This is not wrong. Nature is under no obligation to provide clean, single-cause explanations, but it weakens the explanatory power of the void hypothesis. If the void only accounts for half the signal, it becomes harder to argue that the void is the explanation for the cold spot. It is a contributor, a partial cause, but the anomaly remains partially unexplained, its residual attributed to the same kind of statistical fluctuation that the void hypothesis was invoked to avoid. Beyond the void and primordial fluctuation hypotheses, several more speculative explanations have been proposed for the cold spot. These alternatives do not focus on the Eridanus Supervoid at all, but instead seek entirely different physical origins for the temperature anomaly. Cosmic textures represent one such proposal. Textures are a class of topological defect predicted by certain extensions of the standard model of particle physics. They could form during symmetry-breaking phase transitions in the early universe, events where the fundamental forces differentiated from one another as the cosmos cooled. If a texture collapsed along the line of sight toward the Eridanus region at the appropriate cosmic epoch, it could produce a localized temperature decrement in the CMB with an angular extent and depth broadly consistent with the cold spot. Texture models can be tuned to reproduce the observed signal, but they carry significant caveats. The specific particle physics models that predict textures are not independently confirmed. The parameter values needed to produce the cold spot-like signal are not derived from first principles but fitted to the observation, and no other confirmed signatures of cosmic textures have been detected in the CMB or elsewhere. The texture explanation remains a theoretical possibility without strong independent support. Non-standard inflationary models offer another class of alternatives. The simplest inflationary models predict that the primordial density field should be a Gaussian random field, meaning its statistical properties are entirely characterized by a power spectrum with no higher-order correlations. But inflation is not yet fully understood. The detailed physics of the inflaton field, the hypothetical scalar field that drove exponential expansion, remains poorly constrained. Some extended inflationary models allow for features in the primordial power spectrum, localized deviations from Gaussianity, or spatial variations in the inflationary dynamics. These modifications could produce anomalous cold or hot spots in the CMB that the standard Gaussian framework does not predict. Such models can potentially account for the cold spot as a primordial feature without invoking any foreground structure, but they face their own challenges. The standard single-field slow-roll inflationary model fits the overwhelming majority of the CMB data extremely well. Modifying it to explain a single anomalous feature risks introducing unnecessary complexity into a framework that works beautifully in its simplest form. Furthermore, non-standard inflationary models typically predict additional CMB features beyond the cold spot. If those predicted features are not observed, the model is constrained or ruled out. Current data have not confirmed the secondary predictions of most non-standard inflationary proposals. A more radical possibility occasionally surfaces in the literature. Could the cold spot be evidence for something entirely outside the standard cosmological framework? Could it represent a signal from beyond our observable universe, an imprint from a collision between our cosmic domain and a neighbouring bubble universe in an eternally inflating multiverse? This idea, proposed in the mid-2000s and amplified by media coverage, draws on theoretical models of eternal inflation, where different regions of a vast multiverse nucleate as separate bubble universes. If two bubbles collided during or shortly after inflation, the collision could imprint a roughly circular temperature anomaly on the CMB. The multiverse collision hypothesis is theoretically coherent within certain inflationary frameworks, but it is not testable in the way that the void hypothesis is testable. The predicted collision signatures vary significantly depending on model parameters that cannot be independently constrained. The hypothesis does not make sharp, falsifiable predictions that distinguish it from other explanations, and the Eridanus Supervoid provides a more conventional, observationally grounded alternative that must be fully evaluated before exotic explanations are warranted. the scientific community has largely treated the multiverse collision idea as a provocative theoretical possibility rather than a working hypothesis. It appears in review articles, it generates discussion, but it does not command significant research effort relative to the void and primordial fluctuation explanations. Returning to the void hypothesis, one of the most important empirical developments in recent years has been the application of cross-correlation analyses between CMB temperature maps and large-scale structure surveys. These analyses do not focus exclusively on the cold spot, but instead examine the statistical relationship between CMB temperature and foreground matter density across the entire sky. The ISW effect predicts a specific correlation. Directions with more matter should show slightly warmer CMB temperatures. Directions with less matter should show slightly cooler temperatures. By measuring this correlation statistically, researchers can test whether the ISW effect operates at the amplitude predicted by the standard cosmological model. Multiple studies have detected this cross-correlation at statistically significant levels. The observed ISW signal is broadly consistent with lambda cold dark matter predictions, though some analyses find amplitudes slightly higher than expected. This is encouraging for the void hypothesis because it confirms that the physical mechanism connecting voids to CMB temperature operates in the real universe at roughly the predicted strength. However, the cross-correlation results also highlight a tension. When the ISW signal is measured specifically in the directions of known supervoids, the observed temperature decrements sometimes exceed the predictions from standard linear ISW theory by factors of 2 to 5. This anomalous ISW signal, sometimes called the ISW excess, has been reported by several groups using independent data and methods. If the ISW excess is real, it would have profound implications for the cold spot debate. A stronger than predicted ISW effect could close the gap between the void's expected signal and the cold spot's observed depth. But the ISW excess itself is controversial. Some researchers argue it results from statistical flukes amplified by the a posteriori selection of void locations. Others suggest it might indicate non-standard dark energy properties or modifications to general relativity on cosmological scales. Still others point to potential systematic errors in the galaxy surveys used to identify void positions. The ISW excess remains an active area of investigation without a consensus interpretation. The current state of the void-cold spot connection can be summarized with uncomfortable honesty. The structure is detected, the mechanism is validated, the physics produces a real temperature decrement in the direction of the cold spot, but the predicted signal falls short of the observed deficit by a factor of roughly 2, depending on modeling assumptions. Closing this gap requires either more extreme void properties than current data firmly support, enhancements to the ISW calculation beyond standard linear theory, a coincidental primordial fluctuation superimposed on the void signal, or some combination of these factors. No single explanation has commanded a consensus. The void contributes but does not solve the problem alone. The primordial fluctuation hypothesis removes the anomaly, but at the cost of treating the cold spot as a coincidence. Exotic explanations can be constructed to fit the data, but lack independent support. And the tantalizing hints of an ISW excess, if confirmed, could change the entire picture but remain too uncertain to build conclusions upon. This is where the investigation stands after more than 2 decades of sustained effort. The mechanism is clear, the structure is identified, the physics is established, and the answer remains out of reach. Not because the problem is intractable, but because the quantitative precision needed to distinguish between the competing explanations exceeds what current observations can deliver. Better data is coming. Deeper surveys, more precise CMB measurements, larger simulation volumes. Whether that data will close the case or reveal new layers of complexity remains to be seen. What is already clear is that the cold spot and its possible void connection have exposed a seam in the fabric of modern cosmology, a place where known physics, confirmed observations, and standard theoretical predictions come together and almost work. The gap between almost and completely is where the deepest scientific questions tend to live, and this particular gap has proven remarkably resistant to being closed. There is a specific kind of unease in science that does not come from discovering something terrifying. It comes from discovering something that almost makes sense, a result that sits just beyond the boundary of clean explanation, not wrong enough to discard, not right enough to accept. The cold spot and its possible connection to the Eridanus Supervoid produce exactly this flavour of discomfort, and after more than 20 years of investigation, that discomfort has not faded, it has deepened. Because the longer a well-studied anomaly resists resolution, the more seriously the scientific community must consider the possibility that the problem is not with the data, but with the framework being used to interpret it. The standard cosmological model, lambda cold dark matter, is not a tentative hypothesis. It is one of the most rigorously tested theoretical frameworks in the history of science. It accurately predicts the temperature fluctuation pattern of the cosmic microwave background across angular scales spanning 3 orders of magnitude. It accounts for the observed abundances of hydrogen, helium, deuterium, and lithium produced during the first few minutes after the Big Bang. It explains the accelerating expansion of the universe measured through distant supernovae. It reproduces the large-scale distribution of galaxies observed in redshift surveys encompassing billions of light-years. It passes test after test with a precision that would be the envy of any other branch of science. This is not a model that can be casually dismissed. When something appears to conflict with lambda cold dark matter, the first instinct of most cosmologists is to look for an error in the observation, a flaw in the analysis, or a statistical fluke in the data. These instincts are well calibrated. The model has earned that trust through decades of confirmed predictions. The cold spot does not break this model. Nothing about the anomaly requires abandoning the standard framework, but it lives in a region of the framework where predictions become less precise, where observational uncertainties grow larger, and where the comfortable margin between theory and data narrows to the point where small discrepancies become difficult to dismiss. The discomfort radiates outward from the cold spot in multiple directions simultaneously, and each direction leads to a different set of questions with a different set of implications. Consider the first direction. If the Eridanus Supervoid is the primary cause of the cold spot through the integrated Sachs-Wolfe effect, then the quantitative shortfall identified in the ISW calculations is not a minor calibration issue. A discrepancy of that magnitude in a well-understood gravitational effect, applied to a well-characterized structure using well-tested cosmological parameters, represents a significant quantitative failure. Either the void is more extreme than current measurements indicate, which challenges structure formation predictions, or the ISW effect operates differently than standard linear theory predicts for very large voids, which challenges our understanding of how photons interact with evolving gravitational potentials, or something beyond the standard ISW mechanism contributes to the signal, which requires identifying what that something is. Each of these possibilities is individually manageable. None requires revolutionary new physics, but each one, if confirmed, would force a meaningful revision to some aspect of the standard framework. The void being more extreme than expected would indicate that structure formation produces larger underdensities than lambda cold dark matter simulations typically generate. The ISW effect being stronger than predicted would suggest that nonlinear gravitational dynamics or dark energy physics at very large scales behaves differently than current models assume. An additional contributing mechanism would demand identification and characterization, which could lead anywhere from mundane foreground effects to genuinely new physics. Now consider the second direction. If the cold spot is not primarily caused by the void, but is instead a primordial feature of the cosmic microwave background, then the standard inflationary prediction for the statistics of CMB fluctuations faces a challenge. The simplest inflationary models predict that the primordial temperature field should be a Gaussian random field with well-defined statistical properties. The cold spot, with its unusual depth, angular extent, and temperature profile sits in the outer tail of the distribution predicted by these models. This is not impossible. Gaussian distributions have tails, and features in those tails must occasionally occur. But the cold spot is not the only CMB anomaly. It exists alongside a hemispherical power asymmetry, a quadrupole-octupole alignment, a deficit of large-angle correlations, and other features that individually sit at the 2 to 3% significance level. Each one alone can be attributed to chance. Together, their presence in a single dataset creates a pattern of low-level tension that accumulates across multiple independent statistical tests. The pattern does not rise to the threshold of a definitive detection of new physics. No individual anomaly exceeds 3 sigma significance when look elsewhere corrections are properly applied. But the collective weight of several marginal anomalies pointing in roughly the same direction, toward less power at large angular scales, toward preferred directions in the sky, toward deviations from perfect statistical isotropy, creates a nagging sense among some researchers that the simplest inflationary models might not capture the full truth of the primordial universe. This is a delicate claim to make because inflation itself remains a theoretical framework with limited direct observational constraints. The physics of the inflaton field, the energy scale of inflation, the detailed dynamics of the inflationary epoch are all poorly known. The simplest models work brilliantly for the vast majority of the data. Modifying them to explain a handful of marginal anomalies risks overfitting. Adding free parameters to accommodate features that might be statistical noise. The scientific community rightly maintains a high threshold for accepting such modifications. But that threshold creates its own trap. If genuine departures from standard inflationary predictions exist in the CMB but manifest only as low significance anomalies scattered across multiple statistical tests, the standard methodology of requiring high significance in any single test might systematically miss them. The universe could be telling us something through a pattern of whispers rather than a single shout, and our statistical framework could be poorly equipped to hear it. The cold spot sits at the intersection of these concerns. It is the most visually striking CMB anomaly, the easiest to point to on a map, and the one most directly linked to a potential physical explanation in the foreground void. If the void partially explains the cold spot, the residual primordial component becomes less anomalous, potentially reconciling the feature with standard inflationary statistics. If the void does not contribute meaningfully, the cold spot remains a full-strength anomaly that the standard model must accommodate through statistical chance alone. The void's role matters not just for understanding the cold spot, but for evaluating the health of the standard inflationary framework as a whole. A third direction of discomfort concerns the void itself, independent of the cold spot entirely. The Eridanus Supervoid, if its properties are confirmed near the upper end of current estimates, represents one of the largest coherent underdensities ever detected in the observable universe. The question of whether standard lambda cold dark matter cosmology comfortably produces structures of this scale and depth is not fully settled. Computer simulations of structure formation generate a wide range of void sizes, and the exact frequency of supervoids in the billion light-year class depends sensitively on the simulation volume, the resolution, and the assumed cosmological parameters. Some simulation analyses find that voids matching the Eridanus Supervoid's properties, while rare, are not impossibly so. Others find them in significant tension with the predicted distribution. This tension connects to a broader pattern in observational cosmology. Over the past 2 decades, several large-scale structures have been identified that appear to challenge the expected homogeneity of the universe on the largest observable scales. The Sloan Great Wall, stretching roughly 1.4 billion light-years, the Hercules Corona Borealis Great Wall, reported at up to 10 billion light-years across, though its reality remains debated. The KBC Void, potentially encompassing a 2 billion light-year underdensity around our own cosmic neighbourhood. Each of these structures individually can be accommodated by the standard model through appeals to statistical rarity. but their collective presence raises the question of whether the universe is genuinely more structured on the larger scales than lambda-cold dark matter predicts. If it is, the implications cascade through multiple areas of cosmology. The assumption of large-scale homogeneity underpins the Friedmann equations that describe cosmic expansion. It justifies treating the universe as a smoothly expanding fluid with small perturbations. It allows scientists to extract precise cosmological parameters from the CMB by assuming that the fluctuation statistics are the same everywhere on the sky. Violations of this assumption, even modest ones, could introduce systematic biases into parameter estimates that propagate through every calculation built upon them. The Eridanus Supervoid does not prove that large-scale homogeneity breaks down. No single structure can prove such a sweeping claim, but it contributes to a body of evidence that keeps the question open. And keeping that question open has consequences for the interpretation of the cold spot, because the ISW effect is calculated under the assumption that the void is a perturbation within an otherwise smooth background. If the background itself is less smooth than assumed, the calculation changes in ways that are difficult to quantify without better data and more sophisticated theoretical frameworks. These intersecting uncertainties create what might be called a web of mild tensions. No single thread is strong enough to break the standard model, but the threads connect. The cold spot is linked to the void. The void is linked to structure formation predictions. Structure formation predictions are linked to the properties of dark energy and dark matter. Dark energy properties are linked to the ISW calculation. The ISW calculation is linked back to the cold spot. Pull on any one thread, and you feel resistance from all the others. Resolving the cold spot cleanly requires resolving the void properties cleanly, which requires resolving structure formation predictions cleanly, which requires resolving dark energy behavior cleanly. The problem is not isolated. It is embedded in the interconnected fabric of modern cosmology. Some researchers have explored whether the cold spot could provide leverage on the dark energy equation of state, the parameter that describes how dark energy's density evolves over time. In the standard model, dark energy is a cosmological constant with an equation of state parameter exactly equal to -1. Its density does not change as the universe expands, but observational constraints on this parameter are not infinitely precise. If dark energy is slightly different from a cosmological constant, with an equation of state that deviates from -1 by even a small amount, the ISW effect changes. Stronger dark energy acceleration would cause void potentials to decay faster, enhancing the ISW signal. Weaker acceleration would cause slower decay, reducing the signal. The cold spot's temperature deficit, if accurately attributed to the ISW effect, could in principle constrain how dark energy behaves on the largest observable scales. In practice, the constraints from the cold spot alone are too weak to be competitive with other dark energy probes. The uncertainties in the void properties and the ISW modelling are too large. But the principle matters. The cold spot is not just a curiosity or an isolated anomaly. It is a window into the physics of dark energy, gravitational dynamics, and structure formation on scales where those physics are hardest to test and least well understood. The question of what future observations might resolve the cold spot debate is easier to answer than the question of what the answer will be. Several major observational programs currently underway or in advanced planning will dramatically improve the data available for studying both the void and the cold spot. The Vera C. Rubin Observatory, currently being commissioned in Chile, will conduct the Legacy Survey of Space and Time, a 10-year program mapping billions of galaxies across the southern sky with unprecedented depth and photometric precision. This survey will provide far better measurements of the galaxy distribution in the Eridanus direction, sharpening the void's measured size, depth, and density profile. It will also identify voids across much larger cosmic volumes, enabling statistical comparisons that can determine whether the Eridanus Supervoid is genuinely unusual or merely the most prominent example of a common population. The Euclid Space Telescope, launched by the European Space Agency in 2023, is designed specifically to map the three-dimensional distribution of galaxies and dark matter across a large fraction of the sky out to redshifts beyond 1. Its combination of optical and near-infrared imaging with spectroscopic capability will provide the kind of precise redshift measurements needed to characterize void structures at the Eridanus Supervoid's distance with far greater accuracy than photometric surveys alone can achieve. Euclid's data will allow researchers to construct detailed three-dimensional models of the void, determining whether it is a single coherent structure or a complex of multiple aligned underdensities, and measuring its density profile with enough precision to produce tightly constrained ISW predictions. The Dark Energy Spectroscopic Instrument, which began its main survey program in 2021 from the Kitt Peak National Observatory in Arizona, is measuring spectroscopic redshifts for tens of millions of galaxies and quasars across a 5-year program. Its data will contribute directly to void identification and characterization, including in the Eridanus region, and will provide independent cross-checks on the void properties derived from photometric surveys. On the CMB side, next-generation ground-based experiments, including the Simons Observatory and the planned CMB S4 project, will measure the microwave background with dramatically improved sensitivity and angular resolution. These experiments will refine the cold spot's temperature profile, search for polarization signatures that could distinguish between primordial and foreground origins, and provide better constraints on the ISW effect through cross-correlation with large-scale structure maps. CMB polarization is particularly promising because the ISW effect produces a characteristic polarization pattern that differs from the polarization generated at the surface of last scattering. Detecting this pattern in the cold spot direction would provide direct evidence for a late-time ISW contribution, independent of the temperature data alone. Improved theoretical tools are also being developed. Larger and higher resolution cosmological simulations allow researchers to generate statistically meaningful samples of supervoids and calculate their ISW signals with greater fidelity. Full general relativistic simulations that go beyond the perturbative approach used in standard ISW calculations can capture nonlinear effects that might enhance the predicted signal. Ray tracing simulations that follow individual photon paths through realistic cosmic structures provide the most physically complete predictions but are computationally expensive and only now becoming feasible at the required scale and resolution. These converging observational and theoretical advances create genuine reason for optimism that the cold spot mystery will move toward resolution within the next decade. But optimism about progress is different from confidence about the outcome. The data could confirm that the void accounts for the cold spot through a slightly enhanced ISW effect, resolving the anomaly within the standard framework with only minor adjustments. Or the data could sharpen the discrepancy, confirming that the void's ISW contribution is insufficient and that something beyond the standard model is required. Or, perhaps most unsettlingly, the data could continue to leave the question unresolved, narrowing the uncertainties without definitively selecting among the competing explanations. This last possibility is worth dwelling on because it reflects a broader truth about cosmology at its observational frontiers. Some scientific questions resist clean resolution not because the underlying physics is mysterious, but because the observations required to distinguish between competing explanations are just barely beyond current capabilities. The cold spot might be one of these threshold problems, a question that lives at the exact boundary between what current and near-future technology can and cannot answer. If the void contribution falls in the range of 40 to 50% of the observed signal, and the primordial component accounts for the rest, distinguishing this composite explanation from a pure primordial origin or a pure foreground origin may require measurement precision that takes another generation of instruments to achieve, and this is where the deeper unease finally crystallizes. The terrifying aspect of the cold spot is not that it proves the universe is exotic. It does not. None of the more dramatic alternative explanations explored over the past 2 decades has established itself as a serious contender for the cold spot's origin. The exotic possibilities remain where we left them, theoretically interesting, observationally unsupported, and unnecessary given that a more conventional explanation exists. The problem is that the conventional explanation does not fully work either. The terrifying aspect is not that any single dramatic explanation has been confirmed. It is the opposite. It is that one of the strangest features in the oldest observable light in the universe sits aligned with one of the largest empty structures ever detected, and the combination of well-understood physics applied to well-observed structures cannot fully account for what we see. The pieces are all familiar: general relativity, dark energy, gravitational potential evolution, photon energy conservation, structure formation from primordial density fluctuations. None of these ingredients is new or controversial. They are the standard toolkit of modern cosmology, tested and validated across countless independent observations. Yet when assembled together and aimed at this one specific problem, the toolkit comes up short. Not dramatically short, not catastrophically short, just persistently, stubbornly, irresolvably short. The shortfall between prediction and observation is not a chasm, it is a crack. And cracks in well-tested theoretical frameworks have historically been the places where new understanding enters. The cold spot may turn out to be a statistical fluke combined with a foreground void contribution that together produce an appearance of anomaly where none truly exists. That would be the least dramatic resolution, and perhaps the most likely one. But even this resolution leaves behind the uncomfortable fact that we spent 2 decades unable to prove it. The anomaly endured because the data were always just ambiguous enough to prevent closure. And an anomaly that persists for decades in a field with rapidly improving observational capabilities is not behaving the way a simple fluke should behave. Flukes are usually resolved quickly. They disappear under scrutiny. The cold spot has done the opposite. It has survived every instrument upgrade, every reanalysis, every new statistical technique thrown at it. It has not grown more significant, but it has refused to become less significant. It sits in the data with a quiet stubbornness that unnerves the people who study it most closely. The Eridanus Supervoid shares this quality of persistent ambiguity. It is too large to be easily explained by standard structure formation, but not so large that it clearly violates the model. It produces a detectable ISW signal, but not one large enough to solve the cold spot on its own. It exists at a distance where galaxy surveys are complete enough to confirm its presence, but incomplete enough to leave its properties uncertain. At every turn, the void occupies the uncomfortable middle ground between ordinary and extraordinary. Perhaps what the cold spot and the Eridanus Supervoid are really telling us is something about the limits of cosmological interpretation at the largest observable scales. The standard model works spectacularly well for the CMB power spectrum, for nucleosynthesis, for the Hubble diagram, for baryon acoustic oscillations. These are contexts where the predictions are sharp, the measurements are precise, and the statistical samples are large. But the cold spot is a single feature. The Eridanus Supervoid is a single structure. And cosmology, at its heart, is a science with a sample size of 1. We have one universe, one CMB sky, one set of large-scale structures. When we encounter an unusual feature in that singular dataset, our statistical tools built for large ensembles struggle to determine whether the feature is a meaningful signal or an irreducible fluctuation in a sample too small to interpret with confidence. This fundamental limitation will not be solved by better telescopes or larger surveys. It is a structural feature of cosmology itself. We can improve our characterization of the cold spot and the void. We can narrow the uncertainties on their properties. We can test the ISW prediction with greater precision, but we cannot generate a second universe to see if the anomaly recurs. We are left with the irreducible ambiguity of a unique observation. The cold spot endures because it inhabits this ambiguity with a stubbornness that mirrors the void itself. An enormous region of almost nothing, sitting behind one of the most puzzling features in the most ancient light we can observe, connected by physics we fully understand yet cannot make work quantitatively. The void is there. The cold spot is there. The connection between them is plausible, partial, and incomplete. And the universe, as it has always done, declines to make its deepest answers easy. What terrifies cosmologists is not a proven exotic explanation. It is the quiet persistence of a question that should have been answered by now, but has not been. It is the recognition that familiar physics applied to observed structures can produce a result that falls short of what the sky actually shows. It is the possibility that something about the largest scales of reality operates in ways that our best models approximate, but do not fully capture. Not broken, not wrong, but incomplete in ways we have not yet learned to articulate. The cold spot remains. The void remains. And between them, in the gap that no calculation has yet closed, something about the universe is waiting to be understood.